Hello everybody, my name is Simon Painter, and what I'd like to present to you folks today is a new and fun thing that I found that we can do with .NET and a little bit of creativity. This is me back a year or so ago when I was young and relatively carefree, unlike these days. But I have been a .NET developer for about 15 years or so. Been doing this business rather longer, honestly, than I should be admitting to you, but there we have it. And what I like best of all is finding fun things to do with our code. Finding fun tricks and techniques that we can use to do interesting stuff, to do fun stuff. So today's talk will eventually turn around to the subject of Jane Austen, but for the moment, what I want to talk about is breakfast cereal. So, I have two children, Soph and Kate. They are 4 and 6 years old, and they're awesome and a huge handful, of course, at the same time. And every morning, for some reason, they insist they be fed. Every single flipping morning. And each morning they have a different choice, potentially, of breakfast cereal. And what I want to do here is to try and model the process by which they make their selection of breakfast cereal. Maybe this is to help with us deciding what shopping to do, which cereals to buy as the weekend, something, who knows, but bear with me, all will become clear. Of course, in order to do this, you would have to be some sort of utter weirdo who would spend every single day noting down your kid's breakfast cereal choice, which of course I have done. So this was the choices they made each morning over the course of April. And there's a few things to notice here. For a start, they seem to have a little bit of a preference for Cocoa Pops and Cheerios, but on top of that, they're fairly faddy. They make their choice, and then they stick with that choice for a bit until they're bored and move on to the next choice. That's interesting. And this is some of the behaviour we want to try and capture. But first off, let's put together a few very simple statistics. So, over the course of the month, they chose Weetabix 9 times, Cocoa Pops 11, and Cheerios 10, which is roughly what I observed looking at the thing. So if we wanted to create the simplest, dumbest model humanly possible, we'd do something like this. Yeah, I'm not very good at drawing. But it would be each day we make a choice and we use the number of times that each was chosen in the month of April to make a selection which is weighted based on probability, which is something that we could probably throw together code-wise in the course of 10 minutes or so. And what you get generated by this process, if you were to make a selection for every day again in April, is something like this, which statistically is not unreasonable, but the problem that we have here is that we've lost some of our pattern. These virtual kids that I have just generated cereal choices for, they seem to be much more flighty about what they choose. They seem to constantly be flicking in some cases from one cereal to the next, because there's absolutely no meaning from each day to the next as to what we should choose. There's no memory built into the system. So the way perhaps instead to think about our cereal choices day by day is as states. Imagine that each kind of cereal is a state in the system. Cocoa Pops, Cheerios or Weetabix. When we look at a day where they chose Cocoa Pops, the following day has 3 choices. They could have Cocoa Pops again, or they could shift to Cheerios or over to Weetabix. Similarly, Weetabix. They've got 3 options again. Stick with Weetabix, shift to Cocoa Pops, shift to Cheerios. And again with Cheerios, same stuff. Each state has 3 possible states. Stay the same or shift to one of the other 2 options. So what if we split our statistics so that we modelled the changes in state and how often each of those specific changes occurs? Looking back at our original diagram, this is what we end up with. Weetabix when chosen, became Weetabix again 6 times. It shifted to being Cocoa Pops once, it shifted to being Cheerios twice. Cocoa Pops, similarly, 9 times, having chosen Cocoa Pops, they wanted them again the next day. Twice, they decided they'd rather have Weetabix after instead, and they never ever chose Cheerios after Cocoa Pops. Is that significant? I don't know. Maybe, maybe not. Let us bear in mind that this is 1 month's worth of data, and if I were mad enough to go and capture a year's worth of data, we might get something more meaningful, but for now, let's just stick with the limitations of the system that we've designed. And finally, Cheerios. Cheerios to Cheerios 9 times, Cheerios to Cocoa Pops once. We never went from Cheerios to Weetabix. Again, significant or no? I don't know, but there it is. It is a behaviour that existed. And through this technique, what we want to do is to preserve some of this information about the changes in state as we go around. If you want to see them again as percentages, there we go. So, we've got something that we can act on now. We can make a choice each day based on what is the current state and what is it that we could move to. So if today was Weetabix, then when spinning up the day after Weetabix, let's make it a 66.67 probability that we'll stay on Weetabix and choose them again, or an 11.11% probability of shifting to Cocoa Pops, or a 22.22 to shift to Cheerios. And then we get something like this. Now, this isn't entirely perfect necessarily, but it's not bad given the limited amount of data that we selected. And it has more accurately captured the style of the original data. We've got our faddy kids. I know there's a little bit of a blip around the 1st and the 2nd of the month, but that aside, by and large, we are capturing that faddiness. The Cocoa Pops staying Cocoa Pops for a time and then shifting to something else and shifting to something else. They didn't have a very long stretch at eating Weetabix at any time, so similarly here, we've got short stretches of Weetabix and long of Cheerios and Cocoa Pops, so we've preserved a lot of the original information. And this technique is called a Markov chain, named after this gentleman here. He's a Russian mathematician, I think it was Andrei Markov, and he came up with this concept of the states and the changes in state, and then capturing the probabilities of the state changes. And in order, not everything can be represented with Markov chains. In order to be represented this way, it has to be Markovian. And what does it mean to be Markovian? Well, it has to be discrete. Now, what does discrete mean here? We mean you can't be two at the same time. That means you're A, you're B, or C. You can't be A and B, B and C. In the case of my cereal, that works fine. Running under the assumption that I'm not going to let my kids have 50% Cocoa Pops mixed with 50% Cheerios. For the sake of this argument, I'm saying it's a thing I don't allow. But in principle, you get the idea. One thing or the other thing, not both. It has no memory as such. Beside wondering about the previous day, moving on to the next day, beyond that it has no memory at all. What happened 3 days ago is of no consequence. Only what happened yesterday and what I'm deciding to do today. Markov chains only represent a change in state. They don't tell you what it is or isn't on any given day. It just tells you, given what you were, these are the options you've got, and here is the likelihood that you will go this way or that. This sum is not entirely correct, but the principle is all of the probabilities for all of the options on any given day should add up to 1. As in, there aren't any other probabilities missing somewhere. That means we have captured all possible states together. There's not, in my example, I have the 3 cereals. There is no 4th that I'm not measuring. There were 3 cereals. That represents the entirety of the system. And all of the probabilities for each cereal for any given day add up to 1. That is, those are all of the options. So, what else can we do with this sort of idea? So we've got our weighted probabilities. Can we generate some interesting statistics from this? Well, we can. But in order to actually get to that data, we have to do a little bit of number crunching. Hopefully nothing too excessively complicated. This is a matrix, nothing to do with snazzy looking chaps with long dark trench coats and glasses. All it is a grid. It's a two-dimensional array, same as all the sorts of two-dimensional arrays we've run into in .NET in the past. But to illustrate what each of these items mean, the columns represent the state that you wish to change to, the rows are the state you are changing from, and here I have laid them out in the order Weetabix, Cocoa Pops, Cheerios. You can actually lay them out any order you like, it really doesn't matter, but provided that you're consistent from that point. So every single time I ever reference these probabilities, I'm always going to do Weetabix, Cocoa Pops, Cheerios. So as long as I keep that order, everything works. All of these letters represent numbers, I'll fill them in shortly. Now to actually start running Markov chains, we need two things. First off, we need this. This is our transformation matrix. This represents all the different states and the probabilities of which goes to which. And we also need an initial distribution. This is our seed probabilities. This is the probabilities as of day one that decide our first state. So I don't actually know what that is in the case of our serials. But that doesn't necessarily matter. And especially not with serials, because of course it doesn't matter. But here I am saying that these are the initial probabilities on day one of either choosing one of the three serials. So, in order to decide what it would be, what the probability would be on day one of any of those given serials, as in how does the initial distribution transform from the day one values that I pump in there to the day two values after we've had one pass through the system to make a selection, we have to do matrix multiplication, which is not as complicated as it might sound. All it means is that if on day two I want to work out what are the probability that they will have chosen some Weetabix, all I have to do is to multiply together each of those initial probabilities with the state that would make it happen. So what does that mean? It means choose the probability that it would be Weetabix on day one, multiply that by the probability that Weetabix turns into Weetabix again, because that is the combination of circumstances I need to ensure Weetabix from Weetabix. So that would be x multiplied by a. There we go. The next is assume that Cocoa Pops was chosen, that's y, and the circumstance I need to turn Cocoa Pops into Weetabix, so that I've got my probability with Weetabix again, is to select from the grid the from Cocoa Pops, the to Weetabix, which is the D there. So multiply those together. And the last, again, Cheerios to Weetabix is G, multiply that by Z. So you've got three new probabilities, add them all together. We have the new probability on day two that we will choose Weetabix. Same exact process for the other two, it's just that we're going for a different column in each case. But at the end of the day, what we still get is a new set of probabilities for day two based on whatever it would have been on day one. And if you pump real numbers into it, it looks kind of like this. And this is kind of interesting. So it's saying that there is a lower probability of Weetabix, 0.28, that's 28%. We've got a 34% chance of choosing Cocoa Pops on day two and a 37% of Cheerios. So Cheerios has a significantly higher probability than the other guys. Part of this is going to be because my kids never went from Cheerios to Weetabix, so that will probably bring down the probability for Weetabix. Also, Cocoa Pops can't become Cheerios, so I'm sure that's factored in somewhere. So this is taking into account how likely it is we switch from one state to another, and whether we even can switch from one state to another. The zeros are significant, it's all important. And what we get out is this. And if we want to work out what the probabilities are on day three of any given choice, all we have to do is to replace the initial distribution there with the new ones that we've just worked out for day two, pump it through the same matrix multiplication, and then we get out our day three probabilities. And then for day four, and so on and so on. All we're doing is basically a giant for loop, and we're going around, we're generating a new set of probabilities for the current day, and then going around again using the set that we pre-generated for that day, running it through the same transformation, and then getting out a new set of probabilities for the next day, and so on. And if we pop those into a spreadsheet, it looks like this. So this, day by day, is based on the assumption that there is an entirely even, as in 30% chance for any given serial. Day by day, this is how the probabilities shift as we go along. And there's a couple of interesting things to note here. One is, Cheerios is clearly the favourite by some way in terms of probability. There is ultimately a final probability of somewhere around, I don't know what that is, 44%, something of that sort, biasing towards any given day being Cheerios. So that doesn't mean that every 44% of all days are necessarily Cheerios, but that gives us an idea of the tendency towards shifting in that direction. We also have about a 37, I guess that would be, chance of Cocoa Pops, and absolutely nobody's favourite, right down there at the bottom, Weetabix, about 20% chance that we'll ever get Weetabix. Another thing we notice is somewhere around, I think it's around day 12, the probabilities stop shifting and actually just stay completely constant. This is actually a property of Markov chains. This is how they all and generally always end up. They will eventually find a point of equilibrium where the probabilities stop changing and just continue with the exact same values day after day after day. And that can be an important and significant figure to work out. Now, it doesn't mean that that the states never change again. All it means is that the probability of shifting doesn't change from this point on. Now, this could be useful if, say, what we were modelling was whether someone is likely to claim on insurance, maybe. We could pump in these figures to work out how long does someone have to be a customer before it's the probability that they will have an accident or not doesn't change significantly from this point onwards. This could be useful for marketing, for all sorts of things, to work out when is the period where things are likely to go strange and change wildly to when are they going to be a roughly predictable probability. And just to demonstrate how powerful this phenomenon is, I've then gone and worked out the same thing, but telling it that the initial distribution is 100% for one of the three choices. So I've done it for 100%, the first choice will definitely be Cheerios, but none of the others. Then another one for it will definitely be Weetabix, but not the others, and so on. And these are the charts that we get out. Now, the first between about 8 and 20 days are different in each of these cases. There's all sorts of different things going on. If we start on Weetabix, we have an initial surge for Cheerios, which then kind of calms down a bit. We have some overlapping and taking over. We have, if we start with Cocoa Pops, we actually initially have a massive surge for Weetabix, which then calms down again. But all three charts eventually settle down to the same exact regular predictable probabilities within about, I think about 20 days is the worst that we get, and in the case of the Weetabix, we actually settle down to a predictable pattern somewhere around day 10. So it's always the same probabilities, and you could just run a for loop time after time to work out iteratively when is the point where we actually get a standard regular value. There are some algebra formulae that you can use to work this stuff out without having to do it iteratively, but little admission, I'm not really a mathematician. I just think maths is cool, so this is perhaps more the, as a computer software developer, this is more the way I might go about it, but it's definitely an interesting phenomenon and definitely worth investigating if we're wanting to pull some meaningful data out of our system. So how on earth does any of this relate to Jane Austen? So, Jane Austen, this is her. One of the most awesome novelists in the whole history of the English language. She was clever, she was funny, she was amazing. But possibly, I'm hoping that her sister who drew this picture, which was incidentally the only one ever taken from life, I'm hoping she didn't necessarily really look like this, because right there she looks a bit frowny, or like she's just chewed on a very sour lemon. But possibly she's also put out because she only ever wrote 6 novels. Complete novels, that is. Okay, not getting into the other stuff. I know there are only 5 photos here, the reason being that the last 2 novels were presented as a double bill. So, if we wanted to have some fun with this technique, how can we use it to help Jane Austen to write some posthumous novels based entirely on the stuff that she's already written? Well, we absolutely can do that, and it's not an especially difficult bit of coding. So, let's look at the first page of Pride and Prejudice, which of course has that very famous opening. It is a truth universally acknowledged that a single man in possession of a good fortune must be in want of a wife. So we're going to analyse that particular sentence to demonstrate what I will do to generate a whole load more of this. First, let's focus on the first word, which is rather elaborately drawn there, but it is in fact the word it. So what we would do is search through the whole text, which is available on Project Gutenberg for anyone that wants to have a mess around with this themselves, but look for every instance of the word it, and then see what follows it. And as it happens, it occurs 235 times. That does seem a bit small. That's because I am counting capital I, it, as being different to small I, it, just for the purposes of semantics within the sentence. So, in those 235 instances, what followed it? Well, in 82 instances, it was followed by the word was, in 72 by the word is, and in 11 instances by the word would. So what we would do is to treat it as a state in a Markov chain, and we'll make our selection then based on a weighted probability of based on all of the existing things that followed it, and then choose one of them, clearly biasing of course towards either being was or is. And for the sake of argument, I'm going to say that was what was selected. So we now have it was. And then what we'll do is we'll look at every single instance in the text of the word was to see what it was followed by. As it happens, it wasn't followed by the same thing twice at any point. Not in any one of the 1,843 instances of the word was. And these are all of our options. So we could easily just select one of those at random and then carry on. And if we do that for a whole long amount of time, we end up with a block of text, which looks rather like something that Jane Austen may possibly have written. But it's not perfect. This isn't bad, but anyone who has a close look at this will notice there are a few slightly strange things happening in the text there. There's some strange things happening whenever there is some punctuation. We've got a Mr. there that has nothing after it because the system has become a little confused and thought maybe it was a full stop ending a paragraph. And there's various other problems. We've got and there beginning a line. That's not great. So there's a whole load of strange stuff. So all we have to do is to treat 2 word pairs as being a state. So first off we'll say it was is a state. Then we'll say was a is a state. And so on. Going through the whole of the book, splitting the whole book into 2 word pairs and choosing each one as a state, and then based on that 2 word pair and then whatever followed it anywhere in the text, we have our states that we can move to, and we have weighted probabilities. So we've got a gigantic set of Markov chains. And this is the code that I wrote to do it. So this is a text file containing the text of Pride and Prejudice, and I am going to show you how the code I wrote and how this changes at each stage of the program. So first off, we're just reading the whole thing from Project Gutenberg into our program. No problems. Next, I'm replacing all of the punctuation marks with that same punctuation mark again, but with a space either side of it. Seems a little inexplicable, but there is a good reason. And that is, I want to make sure that we preserve the rules of punctuation throughout this entire text as well. So I am treating each punctuation mark as a word. And I also don't want it to start getting confused and say treating speech mark my there on line 3 as if it were a different word from simply my. So that's another reason I want to do this. And in a moment I'm going to split based on spaces, and by adding a space either side I guarantee that those are treated as words. So first though, I'm splitting on new lines, taking out empty entries because what do we need those for? And so what we end up now is a gigantic array of all of the text of the book, with each paragraph being treated as a separate string inside the array. But it's still only a single dimensional array. Next we're adding BR to the end of, in chevrons, to the end of every line. And I could have chosen any symbol at all. I put that in because in a moment we're going to merge this all together, and I want to make sure that we preserve the new lines, the paragraph breaks, because they are an important part of the structure of this text. Now I've used a sort of pseudo HTML tag there. You can use anything you want. It doesn't honestly matter at all. The only point was to put something in that Jane Austen was unlikely to have written, and which I can replace later when I'm done. So next, I'm going to do a select many, and the select many is selecting against. We have split each one of those array lines into a separate array, split by spaces. So by selecting out into an array split by spaces and new lines, and then doing a select many, we collapse the whole thing into one gigantic single dimension array, where each word or punctuation mark in the whole of the text is an element in the array. So I've got every single word and they're all in order. And that is the raw material that we're going to work with. This block of text is iterating through everything. So first off, it's preserving aside the first two words, and then we're looping around, skipping the first two so that we don't count them again, and then using each of the previous two words at any given point together as the key. We then see, does this already exist in a dictionary, which I've defined elsewhere in the code base? If they already exist, then add them to the count for this key going to this next word. So it is going to A. If we come in against another, so if we look at the data structure I've got on the right of the screen there, if this were to encounter another it is followed by an A, then I would amend that to a 14. Otherwise, if it was it is 1, then we'd add a new element there, which was a 1, which I would give a counter 1 initially, till we encounter it again, and so on. So every two-word pair then has an entry in this dictionary with a data structure following it with all the things that could possibly follow that two-word combination. So far, so good. So then what I do is I transform that data structure, that dictionary, and I convert each individual instance of a possible word that will follow the key into an enumerable repeat, repeating that word as many times as it was ever encountered in the text. So A was encountered about 30 times following it is, so I have literally converted it into 13 instances of the word A in an array, followed by one instance of the word more, 3 of very, because there must have been 3 veries following it is. Which seems strange, but the reason is, now, if I ever wanted to work out a random word to follow it is, which is reasonable and in keeping with Jane Austen's style, all I have to do is to generate a simple random integer based on the length of this array here within the it is entry, and then select one of them at random, and then that will take into account the biasing that should occur towards A because A occurred so many times, and away from more because that only occurred once. So we get a nice, easy way in code to make our random selection. And then all we have to do is to decide on some element, some feature which we're going to use to decide how long we're going to go for. I have done it with a count of how many line breaks we've had, how many new paragraphs. So I'm saying generate me 500 paragraphs worth of Jane Austen. And all we're doing is somehow deciding on a first 2 words, which actually earlier on I haven't shown it here, but I did it based on what were the words that opened any of the chapters. There's about 50 chapters or something like that in the book, so I just extracted the first 2 words of every chapter and then used that as my initial set of things that I select from. And then based on that, look in our set of weighted probability arrays and then select one, and then use that new word plus the one that preceded it as the new key, and then carry on again and again and again until we finally reach the point. And then at the end we replace any BR characters with 2 new lines to make sure that we leave a gap in between. And this is actually what we get at the end. What we get is something that, if you were to read this not paying very much attention to it, it would sort of vaguely scan as being something that looks a bit like something Jane Austen wrote. You've got the right sort of style of writing, the right sort of voice. You have the characters, you have the right lengths of paragraph. It all looks very reasonable. It's just that if you read it, you'll find that it's absolute gibberish. There's no memory. Beyond what were the previous 2 words, there's no more memory than that. Characters will appear and disappear almost at random with no special explanation. There's no story here. There's nothing that knows what's going on. But still, as much fun as this is to read, and it is kind of funny, the point is, though, that I have gone through a whole load of chaotic data, I've extracted pattern from it, and then I've generated something which is statistically roughly equivalent and looks and feels the same, but is in fact random. Now, in the real world, we're never going to really do this with Jane Austen. But where could we use this sort of thing? There. This is a diagram of PageRank. It's used by Google. This is a Markov chain, the system that Google has for going through websites and deciding how to rank pages based on how they connect. That uses Markov chains. So that's not using the simulation feature of the Markov chain, just the modelling, but still, I'm not going to pretend I entirely understand how this works, but that is in essence what it's doing. Predictive text is exactly the same sort of technique as I've been doing with my randomised Jane Austen. That's Markov chains. Finances. This sort of process is used to predict the future of things like how the market will behave, how our customers will behave. And you could decide on whichever factors you want to focus on and then make some sort of prediction on what your customers are going to do next, how they'll behave. You can determine the probabilities of what options they might choose given an amount of time. There's all sorts of stuff that you can gain from this technique. Predicting the future, well, that's kind of ties in with some of the other stuff, but yeah, not quite like these guys, but there's all sorts of future states that you can predict based on your source data. You could use this in testing. You could use this to generate as much random test data of some sort of continuously operating system that you wish, which will have all of the same structure and behavior as the real system that you want to test, but is random and will be continuing as much as you like. You don't actually have to go and capture real live data. You could just and then reuse the same piece. You could just capture it, analyze it, and then generate as much of it as you want. So again, testing could be a nice avenue for this stuff. And finally, of course, potentially we can use it to make poor old Jane Austen happy by continuing her legacy of writing really good books. Sort of. Maybe a bit. And rest. And if all's gone well, I'll now hand over to, well, myself, but in real time. Thank you.